to everyone. As I was introduced, I'm Caldarelli, a PhD student at Sapienza University of Rome. It's a great pleasure to have the opportunity to present my work to you. And I will speak about my work, which is entitled Many-Body Green's Function Approach to Lattice Thermal Transport, which was recently published in the Physical Review B. And I would like to start from some basic concept about lattice thermal transport. So thermal transport in general is a study of the flow of energy in a system in which a temperature, an inhomogeneous temperature profile is present. And so the system naturally generates a flow of energy. In the case of lattice thermal transport, it would be atomic vibration. So it would move the vibrational excitation from the hot side to the cold side of the system in order to recover equilibrium. And Fourier law tells us that the linear transport coefficient that relates the temperature gradient to the heat flux that is generated in the system is the thermal conductivity. And our job as theoretician is to derive an analytical expression of thermal conductivity that can also be implemented in order to give numerical prediction of thermal conductivity in the chosen material. And there are really a great variety of materials that present striking, interesting transport properties. And the classes of materials that we're interested in are the materials with that show ultra-low values of thermal conductivity, so good thermal insulators. And the main motivation behind this is the technological application for these materials. And one of the most interesting to me is the field of thermoelectricity. So thermoelectric materials are materials that can convert heat into voltage via the Seebeck effect, or vice versa, can convert a voltage difference into a temperature difference. It can be used in a variety of applications, such as the so-called thermoelectric power generation. That could be a technology in which the waste heat, which has been estimated that 2/3 of all the energy that is produced in the power generation industry is lost in a form of waste heat. And so this kind of technology could be used to recover part of this heat, of this waste heat, and convert it back into electrical energy, so boost up the efficiency of the power industry. And on the other side, thermoelectric could be used in a technology such as the thermoelectric cooling, in which that could consist in a solid state cooling technology that is based not on harmful chemicals, so it could be environmental friendly. And why do we need a thermal insulator for this kind of materials? Because the thermoelectric figure of merit, which is a measure of the efficiency of a thermoelectric device, is inversely proportional to thermal conductivity. So the best thermoelectrics are the worst thermal conductors, so the best thermal insulators. So apart from this motivation, let's see what are the main theoretical tools that we have to describe thermal transport. The easiest model we can make is the so-called phonon gas model, which is basically an application of Boltzmann kinetic theory to the case of phonon transport, which was first devised by Byers long ago, actually. And it's a picture in which you imagine the phonons as propagating wave packets, so behaving as basically a particle of a gas, and they conduct heat, propagating and colliding just like particle of a gas inside the crystal. And in this theory, you describe the heat flux as a volume average and as a emission over all the basically phonon states, where Q represents the crystal momentum and S the phonon band, of an expression which has a fairly intuitive expression, because you have the energy, so the physical quantity is being carried, multiplied by the group velocity, so how fast this quantity is carried, just like the electrical current is the charge multiplied by the velocity of the carrier. And then you have this statistical factor here, which basically tells you what is the local amount of vibration that you have. So it is basically the non-equilibrium phonon population. And its dynamics is regulated by the Boltzmann transport equation, which is a really celebrated equation of non-equilibrium statistical mechanics, that when applied to the phonon case will describe how the phonon population evolves due to phonon collisions. And the nice thing about the modern software implementation is that all the parameters that are needed to solve this equation can be, so the phonon frequencies, the velocity, and the scattering rates can be computed from ab initio for space walk calculation. So no empirical parameters are needed for this, solving this equation. This theory gives you an expression of thermal conductivity, which basically amounts on a sum of all the phonon states, so testifying the fact that in this theory, every phonon contributes singularly to thermal conductivity. And the single phonon contribution to thermal conductivity is proportional to their specific heat, to their square velocity, and their inverse scattering rate, so their lifetime, basically. Let's try to see what happens if we apply this theory to a class of material that we can call simple crystal, that present typically a simple enough crystal unit cell that results in a few phonon bands that typically are well separated, so well resolved, and they typically show low values of anharmonicity. So the phonon states are really well resolved and distant from one another. And typically, this kind of material are good thermal conductors in general. If you apply Boltzmann theory, Boltzmann transport theory to this class of system, you get oh, my slide stopped. Sorry. Okay, you get really good agreement with experimental data. And it's really a successful theory in describing thermal conductivity in this class of systems. But now, when you apply this theory to the class of materials we're interested in, that are the so-called complex crystal, when you have where you have complicated unit cell structure, for example, in this distorted ladderite perovskite, you have 20 atoms per unit cell, so 60 phonon bands. And as you can see, the band structure is really complicated, and the phonon states are really intertwined. And moreover, you have a large broadening due to strong anharmonicity that mixes the phonon states. You get that applying Boltzmann theory to this kind of systems leads to fails dramatically in reproducing thermal conductivity. And what is understood now is that the Boltzmann theory can only describe a particle-like transport channel, which is called interband phonon conduction, in which basically phonon can conduct heat propagating in as particles, so flowing from one side to the other of the crystal, while missing completely another transport channel, which is important, and it is so-called interband transport, that is related to the wave-like nature of atomic oscillations and can be interpreted as an interference mechanism between two different phonon states. This other transport channel can be included in the quantum mechanical description of the heat flux operator that has the general structure as follows. So it presents a double summation on the phonon band indices. It features a generalization of the group velocity, so a phonon velocity matrix, and then a combination of phonon operators, so the creation and destruction operator of phonons. That when you take in this summation S equal to S prime, you get here basically the number operator of the phonon that tells you that quantifies the excitation of a given phonon, of a given vibrational excitation. So it is basically the quantum generalization of the Boltzmann flux, so it contains, it contains Boltzmann theory. But when you take S different from S prime in this formulation, you get this couple of operators describe a transition from one band to another. And so it describes an interband contribution to the heat flux. The state of the art of lattice thermal transport is that there were two recent theoretical approaches that successfully modeled interband lattice thermal conductivity. So they have developed they have derived an expression for thermal conductivity that accounts for interband contribution. The first one was the one devised by Simoncelli, Marzari, and Mauri, and is based on a density matrix formalism, from which based on the Wigner formulation of quantum mechanics, in which they are able to derive a generalization of Boltzmann transport equation that also accounts for the interband contribution to thermal transport. And the other one was the one devised by Saeva, Barbarinaldo, Donadio, and Baroni, that instead employed a Green-Kubo approach for a derivation of the thermal conductivity that includes interband contribution. And both works were very successful and highly cited works. But the problem is that these two different approaches lead to different prediction for the interband contribution to thermal conductivity, which is strange because you should expect that a physical observable should be independent on the theoretical approach you use to derive it. And so this was the main motivation of our work. So we wanted to understand thermal transport using a full quantum approach, elucidating analogies and differences with different formulation, and try to see if we can derive the expression of thermal conductivity, derive the one approach with the other. and so solving this apparent discrepancy. And while doing this, also examining the description of thermal transport in the so-called overdamped regime of atomic vibration, where the phonon quasiparticle picture breaks down, and I will describe what this means later. So the first issue that one encounters when describing thermal transport is the definition of the heat flux itself, because as an operator it's not uniquely defined, but it's actually defined via the continuity equation. So it is defined once the definition of the energy density is given. But actually, in our solid state picture, the vibration are described in a discrete lattice, which is the opposite, if you want, of a continuous. No? So the real variable on which you have control is the on-site energy. So quantum mechanically, that operator that when summed over all the lattice sites and the atomic species or Cartesian direction will give you the full Hamiltonian operator. And really, you have virtually an infinite possibilities for partition the energy into its discrete parts. But if you make an educated guess and some locality condition are met in the definition of your on-site energy, you can fairly assume that the energy you associate with a given site will only be concerned with the sites that are near your chosen site. And so you can basically make a coarse graining assumption. So you can define, you can pass from the discrete to the continuous version of the energy density by performing a convolution with a given coarse graining function that would be a continuous function that is peaked around near your chosen site and will decay after a characteristic length smoothly. And with this trick, you can derive the definition of the heat flux operator using the continuity equation. And this coarse graining function could be theoretically delicate to define, but actually the point is that if you are interested in the macroscopic heat flux operator, which is the, if you want, the volume average, so the long wavelength limit of the microscopic thermal current, the idea is that was devised first by Arti a long time ago. That the microscopic details of your coarse graining should not matter much if you want to see the macroscopic heat flux. And so this is a procedure in which the heat flux operator can be derived from a given definition of the on-site energy. And in particular, I said that on-site energy can be chosen in different ways, and different energy partition will result in different definition of the heat flux. And in particular, we studied two of those definition. The first was the one that we refer to as the RT definition that will result in the RT flux operator that follows directly from the expression of the harmonic Hamiltonian in the basis of the ionic displacements, momentum and displacement operators, where G here will be the interatomic force constant matrix, and the natural definition of the on-site energy from this expression is the following. So the one that considers the kinetic energy of the given ion you select, and the basically half the potential energy of the elastic bonds your ion is attached to. And from this definition of the on-site energy, you can derive with the algorithm that I described before the expression of the heat flux operator, which features a double summation on the phonon band indices and the combination of the phonon frequencies, the phonon velocity matrix, and the phonon operators. The other definition of the on-site energy you can make is the so-called Wigner definition that follows from the Wigner formulation of thermal transport, which is a little bit less easy to interpret as the one in the momentum and ionic displacement basis, but it follows basically from a transformation, from a canonical transformation of the Hamiltonian in the phonon basis, which basically amounts in defining a new bosonic operator obtained from the projection of the usual phonon operators on the phonon eigenmodes and transform it back to real space. And this operator can be interpreted as the operator that creates or destroys a vibration, which is basically obtained from a linear combination of phonons, such that the resulting atomic vibration will be mostly centered around the ion you are selecting. And this can be proven, and it is described in this reference that I show you here. And from this expression of the harmonic Hamiltonian, a different definition of the on-site energy is suggested, and it is the following. It features these new Cartesian operators and this square root of the interatomic first constant matrix. And using the same algorithm, we can derive a different expression of the heat flux operator that we will refer as the Wigner heat flux operator, that has still feature the creation and annihilation usual phonon operators, but the velocity matrix is defined in a different way. And in fact, the velocity matrices are defined as the, in the case of RD heat flux, as the matrix elements of the gradient of the dynamical matrix, and in case of Wigner, as the matrix elements of the gradient of the square root of the dynamical matrix. And one can show that with this normalization factor, these two matrices have the same physical units, and the diagonal elements S equal to S prime corresponds to the usual phonon group velocity. And another difference between these two operators is that the RD flux operator features some anti-resonant combinations, so some anomalous contribution to the combination of phonon operators, since it has it features a combination of two creation and two destruction phonon operators, which instead are absent in the Wigner formulation. And with these two definitions of the heat flux, we can now apply all our quantum approach, which is based on a formula in which the thermal conductivity is computed as the long-time average of the heat flux autocorrelation function, which would be computed quantum mechanically as the trace over the density matrix of the product of two heat flux operator, that we actually recast in a current-current response function as a static limit of a current-current response function, because we can apply to this quantity all the many body techniques and the Matsubara finite temperature Green's function formalism that can allow us to make some diagrammatic approximation. And in particular, our approximation scheme is the dressed bubble approximation, in which basically we are approximating the two particle, so the two phonon Green's function, as a product of two one particle, so as a product of two interacting phonon Green's function that we compute actually via the phonon spectral density that is closely related to the phonon, to the interacting phonon Green's function, and possess the nice physical interpretation of a probability density of finding an excitation in the interacting system at frequency omega, crystal momentum Q, and band index S. And you can imagine that if the system is non-interacting, the only excitation you can find are excitation at the peaked at the phonon non-interacting frequency, so harmonic frequency. And so in the harmonic limit, this function are delta function peaked at the harmonic frequencies. But when you include harmonicity, those shapes will be broadened by phonon self-energy effect. And so in the anharmonic case, those functions will be will possess a finite line width and will generally have a more broad shape. And so we encode anharmonicity via the phonon self-energy. And in our discussion, we considered the lowest order anharmonicity, so the three phonon scattering processes, and the isotope scattering as a source of anharmonicity. With this description, we can derive an expression for thermal conductivity that contains both interband transport contribution. So it features a double summation under bond indices with a combination of phonon frequencies and phonon velocities. But the most interesting part of this formula is this basically overlap integral between two spectral densities that tells us how to understand whether we can expect to have interband contribution to thermal transport. In fact, if we are in a situation like in the simple crystal cases in which we have two phonon spectral densities that are close to the harmonic case, so are two delta function peaked at two different harmonic frequency, you can understand that when you take S different from S prime, you will have a integral of two delta function with no overlap, and so you will have zero contribution from the interband part. And so this explains why in simple crystal you don't need to describe interband transport, and the Boltzmann theory works so well, because in this situation phonon only propagate as particle, and so only intraband transport is important. But when you consider the harmonicity, so you consider a finite shape of your spectral densities, you will have a finite overlap, and this integral will be in general non-zero, and so harmonicity will enable also a interband contribution to thermal conductivity. So phonon states can interfere, so can mix and interfere from one another and be associated with a wave-like tunneling from one band to the other that the phonon can make in order to conduct heat. And you can imagine that from this regime to this regime, it's not a sharp transition, but you can actually study how much a particular phonon mode will contribute to intraband transport or interband transport or both by studying the frequency and the line width of a given phonon mode. So if you have in a diagram like this, so if you have a phonon mode with a frequency that is much higher than its line width, it would be positioned around here, in which its line width is so small that it cannot mix with other phonon modes and will not contribute to interband thermal transport, but will only contribute to intraband transport, and so will only behave as a particle in the heat propagation. But then, if you increase on harmonicity and you move vertically in this diagram, you reach a certain point in which the broadening of your phonon gets to the value of the average phonon band spacing. And so from this point onwards, of course, it's not a sharp transition, but you can imagine that from this point, the phonon bands will be mixed. And so it will start to contribute to interband transport. Up to a regime in which only a phonon mode will only contribute to interband transport, and so only behave as a wave in conducting heat. But then in this diagram, we also have this area, this gold area here, that is the area of overdamped atomic vibration, in which we have phonons that have a lifetime that is shorter than its period. So the atomic vibration die even before computing a full period. And in this situation, you can imagine that the spectral density will be so broad that you cannot even associate the spectral density with a given phonon mode. And so the quasiparticle picture of phonon will break down. And in this situation, you have to compute thermal conductivity using our formalism that is based on full spectral density, that also can account for complicated shapes of the spectral density. But if you are below this purple area, you can fairly associate each spectral density to a harmonic mode, basically. And so what you can do if your phonon modes are safely in this area, you can approximate your spectral density as a Lorentzian function that amounts in considering no real part of the phonon self-energy, so no frequency shift of your modes, and approximating the imaginary part of the self-energy with the value that it acquires at the harmonic phonon frequency. So you now have a frequency-independent quantity, which is basically consisting in the phonon scattering rate, so the inverse lifetime. In this approximation, the formula that I showed you before for the Wigner choice of the heat flux coincides exactly with the one that was derived in the work by Simoncelli, so we are able to reconcile the same expression for interband thermal conductivity derived from two different theoretical approaches, but still differ analytically from the one that is derived in this other work. And we can compute the differences from different formulation of thermal conductivity, from different definition of the heat flux, or different theoretical approaches, and see whether this difference lead to sizable numerical differences. And for both cases, so for all cases, we get a thermal conductivity which is composed by an intraband and an interband contribution that, when summed, you get a total thermal conductivity that is in good agreement with the experimental data, so it's able to reproduce the thermal conductivity of complex crystals. And it seems that, as you can see, the different definition of the heat flux, of the heat flux that results from the different definition of the velocity matrix and the presence of anti-resonant term give basically small numerical discrepancies. So the numerical discrepancies that we measure in our numerical simulation are basically negligible for all the different results for thermal conductivity. And so this triggers a question about the fact that this could be a result of an invariance principle of thermal conductivity that could be rigid to the details, the microscopic details in which you describe the heat flux. And so one of the questions that is just unanswered from our work and consisting of future perspective is to consider the invariance principles of thermal conductivity. And Ercole and collaborators have introduced an invariance principle of transport coefficient, which is a gauge invariance principle. So if you redefine your energy density by adding a divergence of a bounded vector field, and you can do this because if a bounded vector field will give negligible contribution to the macroscopic Hamiltonian. In fact, in the thermodynamical limit, the divergence of a bounded vector field in this volume integral will only consist in surface terms that will be negligible. The continuity equation basically gives you a structure between the energy density and thermal current that is really similar to a gauge transformation of vector and scalar potential. From this, you can derive, you can do the volume average of this quantity and see that the macroscopic heat flux changes in this way. So the two definition of the heat flux following from two definition of the microscopic energy density are related by a total time derivative of a bounded vector field. And Ercole and collaborators have shown that from these two definition of the heat flux, if you compute thermal conductivity in a Green-Kubo scheme, you actually get the same result for thermal conductivity. So this is known as the gauge invariance property of thermal conductivity. And so our question was, is our numerical consistency a consequence of this gauge invariance? Well, the fact is that the two definitions of the heat flux that we found, so the Hardy and the Wigner heat flux operator, do not seem to fit into the scheme. So the two definitions of the heat flux, the Wigner and the heat flux, doesn't seem to be connected by a gauge transformation. So their difference is not a total time derivative of a bounded vector field. And so the question is the numerical consistencies consistent between our result a consequence of a broader invariance principle of thermal conductivity that is yet to be theoretically formulated? This is really an interesting question that is left unanswered by our work. And so this would be all. In concluding, let me acknowledge my team. So I want to thank my thesis advisor, Professor Lara Benfatto and Professor Francesco Mauri from Sapienza University of Rome, and then the team of PFL, Dr. Michele Simoncelli, that is now at University of Cambridge, and Professor Nicola Marzari. I'll leave you here my email address if you want any details of any references that you want. And so that's all. I thank you for your attention.
Thank you very much, Giovanni, for this very clear talk. So we have now time for questions. So if you have a question, please raise your hand virtually. I see there's a question by Shavdar.
Can you hear me?
Yes, we can hear you.
Yes. Thank you. Thank you for pronouncing my name correctly. Thank you for this very interesting talk. Please, I have a technical question.
Okay.
Maybe a silly question. If we can go back to slide 11, I think.
Okay. 11 here.
Yes.
Okay.
So if we first of all look on the left, the current operator.
Okay.
On the left, I was wondering whether it's Hermitian. It's not obvious because the second term in square brackets is certainly not Hermitian.
Well, okay. So it is a Hermitian. You can demonstrate it using some of the properties of the velocity matrix. That is when you consider the Hermitian part of this term, you have to consider also the Hermitian of this matrix. So you have to invert the S and S prime indices, and you also have to consider Q into minus Q. So into this, so if you do this transformation, you can see that you can prove that the phonon velocity matrix is antisymmetric, so it's anti-Hermitian if you want. And so this change of sign, basically, when you consider the Hermitian conjugate, maps you this term into this, and so you can show that the this term is Hermitian.
Okay, thank you. And I have an analogous question. In the second column on the right, please.
Okay.
But now it refers to the Hamiltonian little h hat. Again, same question. Is it Hermitian?
No.
So what do you do?
You got me. No. It's actually I have. Well, this was the busiest slide, so I didn't report the actual expression that we use. Because I thought it was confusing, but we actually considered this term, one half of this term plus its Hermitian conjugate.
I understand. Okay.
So I just thought it was confusing too.
Okay, yes.
You're right. This is not actually, it's just one half of the on-site energy that we use.
Yeah. Okay. Thank you.
You're welcome.
Thank you. I have a question myself, a very basic question. So I'm not an expert on this heat transport, but more on let's say electronic excitations. And there, of course, conceptually the interband and intraband are not very different from each other. I mean, apart, of course, from the numerical aspects and the approximations that we do to the interactions. So I didn't completely understand where this problem for the conceptually, let's say, to define this heat flux for the interband part comes from, because if I understood correctly, for the intraband part, everything is clear and there's not more than one definition. So why this is the case? Could you maybe repeat?
Yeah. Okay. So in general, you always have a problem of definition of the heat flux, apart from the distinction in inter and intraband terms. And the fact is that I would say that there are two separated aspects. So the intraband part, so the Boltzmann contribution to thermal conductivity, is well understood and works well. And when you consider the easiest definition that you can make of the heat flux, which is this one, okay. But then the fact is that when you consider a general definition, so the problem is the starting point. So the people actually start from this definition of the heat flux, okay, try to compute the thermal transport properties, and they end up with a thermal conductivity that does not account for interband transport. Then what you do is you go back and try to redefine heat flux operator, and you find that if you define carefully the heat flux operator, you also get interband terms. Okay, and the problem is that the indeterminacy in the energy density results in an indeterminacy in the heat flux operator that seems to left unchanged the intraband part, but the interband part can be actually different depending on the choice of the on-site energy that you make. I don't know if I made myself clear.
Yeah. Okay. Yeah. Thanks very much. Yes. Thanks. Are there other questions? Valerio has a question.
So can you hear me?
Yeah.
Okay. So my question is about, let's say, the anharmonicity that you say that you represent by a self-energy which is going to dress the phonon propagator.
Yes.
However, I mean, you have shown also, you introduced this term, but you are not shown, let's say, a form of this self-energy. At the end, let's say this part, this anharmonicity, you take into account by that Lorentzian approximation in which you introduce a broadening,
yes,
which is not calculated ab initio. So you are not really calculating.
No, it's calculated ab initio.
How?
Yeah, it's calculated with some. Well, there are some software implementation when you can compute from a supercell approach the third order first constant matrices. So the other expansion on the so the first order expansion after the harmonic approximation, you can compute the third order for coupling constants between atoms, and from that you can obtain the
and do you have in your slides, let's say, a formula showing how these third order matrix elements enter into play into the self-energy?
No, I don't have a slide, but it's basically computed at the lowest perturbative order. So it's basically a Fermi-Gordon rule for the for the anharmonic interaction Hamiltonian. So it's like considering the first order anharmonicity, so the third order interatomic first constant matrix as a perturbative Hamiltonian, and you can do perturbation theory, and using Fermi-Gordon rule, you can compute the scattering rates from that anharmonic Hamiltonian, so from that interaction Hamiltonian, and the formula is and it's the easiest formula you can make, basically.
Okay, and so you take into account this effect, so
yes.
Phonon scattering, and what about, let's say, the isotopic effect? So this is a kind of impurity that you have to introduce in there, and also if you take into account also the electron-phonon coupling, which is also going to provide you, let's say, a self-energy effect on your phonon propagator. So do you take into account this electron-phonon coupling in your approach?
No, we didn't take into account electron-phonon coupling because typically these kind of systems are insulators, so they have a gap that is fairly wide. So in the range that is wider than the available phonon energy for electron scattering. So we don't take into account this kind of effect, considering that it is negligible. It is true that if we want to use this kind of systems in thermoelectric application, you should consider this kind of system when a doping is present.
Exactly.
And when you consider doping, you should also take into account electron-phonon interaction. But let's say that the strength of our approach is being based on a phonon self-energy. You have a precise prescription on how to include other scattering effects on the phonon propagator. So we didn't take into account electron-phonon, but we could actually. So.
And what about the isotopic effect?
The isotopic effect, we take into account isotopic effect in the natural occurring isotopes in a crystal that are tabulated in a database. I can give you the reference on the details of the calculation. And so those kind of effects are considered, but there are only let's say intrinsic defects, so natural occurring isotope concentration, and not extrinsic defect scattering. We don't have a model for that.
Okay, thank you. Thank you, Valerio. In your results for the thermal transport coefficient, you showed the results for the using the definitions for the heat flux of Hardy and Wigner, and also of this work of Isaev.
Yeah.
Yes, and which basically overlaps with the results obtained with this definition of Hardy, I think.
Yeah.
Was it because they used exactly the same?
Yeah, they use exactly the same definition of the heat flux, but they actually introduced the phonon self-energy, so include an harmonicity in a slightly different way. So we derive for quantum approach we introduce an harmonicity via the spectral density, so via the phonon self-energy, in a frequency domain, as it is the common way of doing in full quantum approach. Instead, they basically use an assumption on the real time. So they basically introduce anharmonicity as a scattering rate directly on the real-time expression of the Green's function. This should be equal, but there are some some analytical differences that could be shown to be negligible in some regimes, but we actually end up with two different analytical descriptions. That it seems that in these materials lead to small numerical differences, but in general, it is not provided that these differences will be small.
So you mean that in these two cases, the results are basically the same, but it's not guaranteed that this will always be the case. No?
Yeah.
Okay, I don't see other questions. Maybe so. Just one question on the numerics. So for these kind of systems, how expensive are the calculations?
Okay, so they are fairly expensive. So the probably the two main numerically expensive part of the calculation is the relaxation of the structure of this complicated unit cell. So when you have a complex crystal with this really complicated unit cell, it is fairly expensive to compute do the non-self-consistent calculation to relax the structure. And another really important bottleneck is the computation of the third order first constants that will require a large number of atoms typically to compute. But there are some schemes, some tricks to speed up the calculation. So the third order first constants are computed using finite difference methods. And in particular, in this case, we have used the Cheng-Bittier code, in which you can compute the third order first constants from a finite difference method that also exploits crystal symmetries to so you first introduce a real space cutoff, so you consider triplets of atom only in a given cutoff radius that you can study the convergence of, and then you can exploit the crystal symmetries in order to find the non-equivalent triplets of atoms in which we have to compute the third order first constants. And from this kind of calculation, you can derive all the third order first constant matrix elements that you need in order to compute the anharmonicity, so the scattering rates of the phonons. Those are the really two expensive part of the numerics.
Okay, do the results depend a lot on the ground state geometry that you start from? The equilibrium geometry? I guess with different, I guess you use DFT to the,
yes.
Yeah. I just wonder if small differences could be important for your.
I don't know. I don't have a clear answer.
I have no idea.
Okay.
Okay, last chance for questions. Mathieu?
I had a question for all the electronic Green's function people. If they had suggestions about the overdamped regime, if there was some kind of equivalent plasmonic or something like that regime for electrons in which we could go and grab some ideas about what to do with the many-body stuff for phonons.
So you're saying, if I can make a comparison with the electronic case for the overdamping regime.
No, it was more a question for the others if they can give us some useful.
Okay. So
you have an idea, of course.
Probably. So I'm not really an expert, but I can try. So the idea is that you are in the overdamped regime when you cannot safely associate. So you have a spectral density that is so broad that you cannot associate a quasiparticle peak with your spectral density. And this can happen if you have large broadening, but also if you have a multimodal spectral density. So, for example, it is the case of satellite peaks that I think can also happen in electronic Green functions, so spectral density of electrons. That are also, there is also an equivalent of satellite peaks for the phonon case. And in that case, it is not safe to associate so to do a Lorentzian spectrum function approximation, which is basically a quasiparticle approximation to the phonon mode, because there could be cases in which you cannot safely associate a spectral density with a particular phonon vibration. I don't know if this helps the comparison with the electronic case.
Yeah, no, I agree, but when it will be a problem, I agree. Your expression with the spectral densities can deal with that.
Yeah.
I was wondering if they had other ingredients in electron spectral functions and electronic approximations to the self-energy, which kind of go further in that direction. And maybe in your expression, if you go back to your Kubo expression, which has the spectral densities, it's never a problem in defining the velocities, because those feel like very particle-like objects.
Yeah, there is a really interesting question. So the idea is that the fact that the velocities are not changed by the interaction, if you want, and the addressing of the exponent self-energy follows from our approximation, so our adjusted bubble approximation. In fact, you can interpret this formula as basically a bubble in which you have two bare vertices, and the vertices are the velocity vertices, and then this part here consists in the phonon propagator. So in order to trace the velocity and so consider a generalized non-quasiparticle velocity matrix, you should also have to consider vertex corrections to the phonon bubble that you compute in order to consider thermal conductivity. So in our approximation, we don't have, so we still retain the velocity matrix with the, so we still associate the velocity matrix to each phonon, even if it is a matrix. So it is not quite associated with a given phonon, but rather to two phonon bands. So it has a matrix element in different phonon bands. But in order to generalize the concept of velocity matrix, you should also include vertex correction in your description.
Thanks a lot.
If I can intervene, Aryan?
Sure, yeah.
But this formula is not the most general one of thermal conductivity from spectral density formulation, because in fact you are using in this formula again the phonon frequencies, omega of q, and the velocities. Yes. So in the case in which you have a situation, completely damped situation, so you are not able anymore to identify a phonon branch. So you don't know what to write in place of omega of q and in place of v of q. So in order to have a very general formula of thermal conductivity from spectral density, you should always have a formula relying on the b, which is the spectral density of
in fact,
so yeah.
No, it is not the most general possible.
Yeah, but you cannot treat the overdamped regime. You cannot treat by this, because in the overdamped regime you cannot. You don't know what to write in place of omega q and the v of q. You know what to write in. It's not a question of only of vertex correction. So here replacing the bubble plus free vertex function. It is also that you have to get rid of omega of q and of v of q to have a very general formula applying also in the case in which the phonon are completely damped.
Yes, I guess so. So the fact is that probably, it's not the most general expression that you can obtain of thermal conductivity. It's an expression that follows from the the dresser bubble
Yeah,
approximation, which
okay.
is the easiest basically
Yeah,
approximation
let's
that
say
you can
that
do.
you should
the-
always keep the concept of quasi-particle. So the B of Q should be
Yeah.
I mean it should be damped, but I mean you should be able to identify.
The fact is that when you consider vectors, so the real vertex that the real vertex that we should consider is actually a vertex when since it is a energy current correlation function, the real vertex is actually omega times the velocity. So you can expect that when you dress the vertex, you can get an expression of the vertex that in place of the phonon frequency and the phonon velocity will have a complicated structure that we can interpret as a corrected vertex, so a non-quasi-particle energy vertex in this sense. So it is true that this is not the general, the most general expression for thermal conductivity in terms of the spectral density, but is the simplest approximation that we can do in order to still retain analytical calculation, basically.
Okay, thank.
Okay, I don't see any other questions, so I guess this is a good point to stop. So thanks again, Giovanni. Thanks to all of you for joining, and see you next time. Bye-bye.